So our first speaker will be Emanuele Bevacqua, who did his PhD at the Helmut Center for Ocean Research in Kiel and the Wegener Center for Climate and Global Change at the University of Graz, where he also worked as a postdoc before joining the research group of Ted Shepard at the University of Reading. He's a member of the Damocles Cost Action on compound extremes, and his recent work is focused on drivers and trends of coastal compound flooding, about which he will also talk today. And we are very happy to have him presenting right now. And with that, I give the virtual mic to Emanuele. Excellent.
Yes, I'm here. I'm sharing. Can you see the screen already?
I can see the screen. If you would
Indeed.
now go to full screen.
Ah, you can see the screen. Okay.
Yeah.
Okay, it's fine. Yeah. Okay, so great. Not visible yet.
It looks good.
Ah, looks good. Okay, yeah. Okay, great. So thanks for inviting me to give this talk. Very nice. So I'm going to talk, as you said, about a paper that has that is in press actually. So in Communication, Earth and Environment. So if you're interested in more details, you can go through that in the next weeks, I hope, or contact me in case. And the title of the work is More Meteorological Events That Drive Compound Coastal Flooding Are Projected Under Climate Change. So I would like to start with talking of an example of compound flooding through an event that occurred in 2015 in Ravenna, Italy, which is located here where there is this yellow spot on the map. Basically, this event was driven by a low pressure system which drove a storm surge along the coastal area of Ravenna. And this was driven by the low pressure itself and the associated wind with the cyclones, basically. Alongside that, there was a large amount of precipitation, which is shown here by, let's say, magenta and on the map. And as a result of the combination of these two events, fluvial and fluvial water was partially obstructed from draining into the sea by the storm surge, and this caused what is called a compound flooding. Now, there are some more mechanisms causing compound flooding. And in general, we can say that the potential for flooding from inland rainfall can be enhanced by the storm surge, which is obstructing the drainage of the fluvial water into the sea, similarly to what we have just seen for Ravenna. This can be also associated with pluvial water, so something that doesn't necessarily need to happen along big, large deltas. And also, you can have that the flooding from a storm surge can be amplified by precipitation falling on top of the area that is already inundated. And all these events, these mechanisms lead to so-called compound flooding. So related to mechanism one in deltas, there is a paper which has been just published in Nature Communication from Edmonds et al., which is related and interesting in this context. They highlighted that 340 million of people, so about 4.5% of the global population, live on river deltas, and they are really exposed to largely to flooding. And they indicated that compound flooding should therefore considered when assessing the risk of flooding in deltas indeed, because these are areas exposed to such a compound hazard. So within this context, what we want to do is to analyze the compound flooding potential for fluvial and pluvial mechanism globally in present and future climate, and we will do that through focusing on the meteorological drivers of compound flooding, rather than really looking at the flooding itself. That's why I talk about compound flooding potential. So to do so, we use data from ERA interim and 6 CIMIC 5 model for past and future climate. We consider accumulated rain precipitation over 3 days and the meteorological tide daily maximum. The meteorological tide is the superposition of storm surge and wave component, which are both obtained through hydrodynamical modeling based on wind and sea level pressure fields. So the methods we use in practice is to look at return period, which is the inverse of the probability of concurrent precipitation and meteorological tide extremes that are defined as events occurring on average once every year. So to obtain this return period, we need a probability density function of the pairs meteorological tide and precipitation, and such a probability density function, we fit that this PDF through considering only the tail of the distribution to get a more accurate assessment of the return period. And such a PDF is estimated based on generalized Pareto distribution and copulas. So we can give a look at the result for present climate. So this is a map of the present day return period of concurrent extremes. And when we have a more reddish color, basically there is a higher potential for compound flooding. So there are more frequent concurrent extremes. So these low joint return periods indicate, therefore, that there is a higher dependencies between the extremes that we are considering. Overall, the median return period is of 17 years here in this map, which is about 20 times higher than what is expected under independence between the drivers. And on top of such a widespread dependence, there is a large spatial variability in the map, as you can see. So there are for sure some physical processes which are shaping this overall spatial variability in the compound flooding hazard. So which are these physical processes? This is what we are going to look at now. So in general, even though extreme precipitation does not necessarily require cyclones to occur, storm surge does, and as a result, concurrent extremes need to occur basically due to cyclones themselves. And this is shown in practice in these plots, which are composite maps for days when we have concurrent extremes for different locations worldwide. So the location is highlighted by the red dot. The white hazel line shows the sea level pressure, the mean sea level pressure field over days with concurrent extremes. And you can see that all these concurrencies are associated with some kind of cyclonic configuration. So saying that, if we look again at the map seen earlier, so the concurrence probability map or return period, we have as a result that basically the higher compound flooding potential, so where we have red here, is located where there is a higher frequency of cyclones. And this is shown in the bottom panels, where we have the track density of extratropical cyclones and on the right, tropical cyclones. For example, in the equator, we have low cyclones, as we know, and in this area as well, we have a low frequency of concurrence between meteorological extremes. An interesting bit here is, for example, the fact that there is a higher compound flooding potential on average over the northern hemisphere than in the southern hemisphere. And this is in line with the fact that in the northern hemisphere, there is a larger fraction of the coastline, which is experiencing high cyclone frequencies. However, there is not, of course, a perfect association between cyclone frequencies and compound flooding hazard. There are other mechanisms. In fact, high cyclonic activity does not always imply high probability of concurrent extremes. For example, there are some areas where precipitation extremes are not driven by cyclones. And in this case, this precipitation extreme cannot concur with storm surge because the storm surge is caused by cyclones. And in this case, we have a low compound flooding potential. Also, we can have a situation where there is an high cyclone activity, cyclones drive precipitation extreme, so you might expect high compound flooding potential, but instead we can find a low compound flooding potential if precipitation extremes and meteorological tide extremes are driven by different types of cyclone. This is shown, for example, in Finland. Here we can just focus on these two panels. In this location with a red spot, we focused on days where we have extreme meteorological tide, and we have a cyclone located in the northern part of the dot. And instead, when we have extreme precipitation, the cyclones are typically located more in a southern part. These are different cyclones which drive the different extremes, and therefore the two extremes cannot occur at the same time. And this is a result which is based on what Andrew et al. Showed in a previous studies for UK, actually. So a question we can ask now is when do concurring extremes happen? And this is a map showing the answer. This is showing basically the month where there is a higher concurrence of extremes at different locations worldwide. And in line with the cyclonic activity, we see, for example, that in the extratropics, concurrent extremes tend to occur in autumn, winter, when the cyclonic activity is the highest. And in the tropics, instead, we have that this concurrent extreme occur mainly in the tropical cyclone season. On the right, instead, we are looking at the duration of the, let's say, compound flooding season. That is the period where it's more likely to have concurrent extremes. And this season is the longest, for example, in the US here around, let's say, New York. And this is in line with the fact that there, concurrent extremes are caused both by tropical and extratropical cyclones, which occur over different seasons. So a last bit about the seasonality of concurrent extremes is shown here. We have again the map of the present day return period of concurrent extremes here. And we have here the lag between the precipitation and meteorological tide extreme peak season. There is a kind of match between these two maps in terms of color, and this is indicating that, surprisingly in a way, the areas where there are low concurrence probability, so in bluish here, are those where in these areas, precipitation and meteorological tide tend to happen in different seasons. So this is not something that is required. You might have simply that there are no concurrent extremes, but simply that these two extremes occur in the same season, but not in the same days. Instead, they really tend to happen in different seasons, which is something that might be interesting to explore even more. We can go now talk a moment about the compound flooding potential in estuaries, which is something that I was saying we are kind of assessing based on this analysis, based on precipitation. And this is a kind of proof of that, because in fact, so through precipitation, we are providing an estimate of the large-scale compound flooding potential from fluvial processes, obviously because we are considering precipitation. But also we are looking at compound flooding potential in estuaries of medium and small size rivers, which are actually rivers where we have seen that the compound flooding risk tend to be the highest. And also these are most of the rivers in the world. And this is shown by this map where we are comparing the concurrence probabilities of precipitation and meteorological tide extremes in the first plot, so what we have seen so far, more or less. And on the bottom side, instead, the concurrence probability of river discharge and meteorological tide extremes. And the two maps are largely similar at a large scale. Of course, there can be some differences, obviously, especially in rivers which are very long. But overall, the comparison between the two is indicating that the assessment based on precipitation can provide information also on fluvial processes. And this is a result of a study that we have published in Natural Hazard and Earth System Sciences. Said that, we can now give a look at future climate. So we can say that in the future, sea level rise will increase the compound flooding potential basically everywhere, almost in the world. This is kind of expected. What we want to do, and this is shown in the map where we have the decrease in the return period, which is shown in red here. And what we want to do instead here in the next part of the presentation is to show that actually changes in the compound flooding meteorological drivers, so precipitation and meteorological tide extremes, will affect the compound flooding potential beyond the expected effects of mean sea level rise. This is shown here, where we look at the changes in the concurrent, in the return period of concurrent meteorological tide and precipitation extremes without considering sea level rise. And you can see that there are large areas where there is an increase or decrease of the compound flooding potential. In particular, we can see some dots where there are some gray background area in the location. This is basically indicating that the multimodal median change, which is what we are showing here, is large compared to natural variability, and 5 out of the 6 models we are considering agree on the sign of the change. These changes are particularly large over the northern part of the northern hemisphere, which is shown here on this plot, which is indicating the coast fraction where there are large changes compared to natural variability. There are, of course, also areas where the compound flooding potential is decreasing, especially in the subtropics. Overall, over 60% of the domain, the compound flooding potential is increasing, and the median change in the return period is minus 20%, which corresponds to concurrent extremes being 26% more likely on average in the future. You can see also some areas where there are some magenta points, and these are basically where we cannot say what's going to happen due to the fact that some models are projecting a large increase and others are large decrease in the projections. So there are basically large uncertainty there. So we can now think of the drivers of these changes. So the changes can be driven by changes in precipitation extremes, or changes in meteorological tide extremes, or changes in the statistical dependencies between the two variables. Here we ask, how would the component flooding change if we took into account only changes in precipitation extremes? We get this map, which is kind of similar to the map we have seen before. So this is indicating that precipitation indeed is an important driver of the changes that we will have in the future, according to projections. And these changes are largely positive, actually, and this is in line with the fact that there will be an increase in precipitation pretty much everywhere due to a moister atmosphere. On top of that, there will be anyway also changes in the atmospheric circulation, which will reverse this thermodynamic effect in some areas of the world, for example, in Southern Africa, Northern Africa, Australia, and some parts of Southern America. Now we can ask in the next slide, instead, what are the changes in component flooding that will be driven by changes in meteorological tide, and we get this map. So overall, in this map, we have changes that are relatively small compared to natural variability. Anyway, these changes are still pretty much homogeneous, and we can link them to documented change in the cyclone activity based from previous studies. So you can say that there will be some changes in component flooding due to changes due to anthropogenic effects. For example, here we have a northward shift based on other studies of the jet, which is in line with the increase that we have in meteorological tide driven changes, or in the southern part of Europe, where there will be a weakening of the storm track, and we also find such an effect here in meteorological tide changes. So we have basically seen now the changes in component flooding driven by meteorological tide and precipitation, and we have actually found that there is a relationship between the changes in the two variables. You can think, for example, of areas where there will be a strengthening of the regional cyclone activity. In this area, you would expect to have an increase both in meteorological tide and in precipitation. Vice versa, in an area where you will have a decrease of the regional cyclone activity, you will expect a decrease in both of the variables. In fact, when we look at the scatter plot, which is showing basically each location is a dot here, and this is showing the relationship between precipitation and meteorological tide related changes. And you can see that the location where meteorological tide increase, also in this location, also precipitation increase, and vice versa. We have something on the other end of the scatter plot. So there is a positive relationship between the changes in the two variables. And on top of that, there is a kind of offset. And this is due to the fact that precipitation anyway will kind of increase everywhere due to thermodynamic effects. So this effect is a kind of interesting and might have actually some relevant effect in the future. In fact, it may enhance both positive and negative trend in component flooding relative to a situation, compared to a situation where instead there is no dependence between the changes in precipitation and the meteorological tide. Because if there was no such a dependence, you would have that in a certain location only, for example, precipitation would increase, but not meteorological tide. In this case, instead, it seems that where one increase, also the other increase, and therefore the two combine each other to enhance the overall increase in component flooding. This has an effect that, we haven't investigated too much in detail. We stopped to this graph, but it could be interesting to look at this more in detail in further studies. Okay, so we can now think about the third ingredient, so that may drive changes in component flooding, that is changes in the statistical dependence between meteorological tide and precipitation. So this is a map which is showing how indeed component flooding will change because of changes in such a statistical dependence. What we see here is that there is not a clear spatial pattern in the changes. There are compensating changes at a global scale. So there are alpha of the location showing an increase and alpha decrease in the component flooding due to changes in the dependence. probably large ensemble simulation may help to better disentangle any anthropogenic effect in this star. We refrain from interpreting these changes from a physical perspective because we cannot link to known processes, and the map is clearly pretty noisy. This is interesting in line in view of, for example, the study from Valle et al., who found a recent increase in compound flooding over the US coast in the recent decades due to changes in the dependencies. We cannot find anything along in line with these results for future projections. So that's what we find. Oh, sorry. Instead, what we find is that the changes in the dependencies are an important driver of the uncertainties that we have in the future projections of compound flooding. But this is a map which is showing the relative contribution of precipitation, meteorological tide, and dependence uncertainty to the overall uncertainty that we have in the projection of compound flooding. And what you can see is that, for example, here at a global scale, the evolution of the dependence dominates basically the overall uncertainties. It's about more than 50% of the uncertainty are driven by changes in the dependencies. And this is a behavior which is pretty much there for also the single location, single regions. So considering the variability of the dependence is crucial to avoid overconfident, both present and actually future risk assessment. This is some kind of message you can learn from this plot. And concluding, so this estimate should not be interpreted as an assessment of the actual risk of compound flooding, of course, because the actual risk depends on hydrology, exposure, protections. Also, the results should be interpreted carefully for the regions in the tropics, where basically simplified models cannot well simulate tropical cyclones. I mean, we have adjusted the tropical cyclone driven variables in the analysis, but not in projections. And overall, the flooding will increase by 26% globally, and by 106% at latitudes above 40 degrees north. And adaptation planning should not only consider sea level rise and extreme sea level changes, but also compound flooding in future assessment. And maybe another interesting thing to take into account is that there are some areas where concurrent extreme do not lead to compound flooding because they do not interact, but still increasing concurrencies could be challenging, and therefore should be considering for taking future emergency response actions. And with that, I finished.
All right, thank you very much, Emanuele. So now we'll come to our 8 or 10 minute question and answer discussion period. Does anyone have any questions off the bat? If not, I'll ask a quick one to start. And yeah, as a reminder, use the raise hand or, I guess unmute yourself or type it in the chat box. Any one of those 3 things. My question was about if you, or I guess if anyone really has looked at the spatial size of these events. And I know in many basins here in the US, compound flooding and the worst flooding often occurs when there have been sort of 2 events, maybe at different times, but they run down the rivers and combine at a river junction, and then cause a major flood on the large river downstream. So.
Well, in terms of spatial extent, I am aware of a recent study, but it's only based on present day data, so basically on the data from the past, where they looked at a spatial footprint of storm surges. And they highlight that this is a relevant thing to take into account, because of course, if if extreme events occur simultaneously at multiple locations in the same region, or the overall impacts can be enhanced by the fact that, for example, also rescue team might be overwhelmed and you have no time to respond to that, or that in general resources are limited to cope with multiple extremes at the same time. In terms of precipitation, in terms of flooding, there is also something that has been done in terms of river flooding for the past. I'm actually now working on this for precipitation extremes. I'm really looking at spatial extension of precipitation extreme, also looking at future projections. And I'm not aware of anything like that in terms of compound flooding, but it would be actually interesting to try to link the spatial extension with occurrence of compound flooding, sure. Especially all over large basin, an increase in the extension might then contribute to an increase in the resulting river discharge over at a coast, basically. And this may combine with storm surge. Yeah, something that's to look at.
Yeah, thank you.
I had another question that might be easy to answer, but maybe just impossible to answer. The model disagreements in the tropics, is that just a lack of data as usual, or just, yeah, what's behind there? Are the dynamics not known, or?
Yeah, it's a very interesting question. I don't really have an answer to that, to be honest. It wasn't really possible to explore it because we have only six CMIP 5 models, because basically we are using storm surge, which is available only from these models. These are just the data that exist. And it wasn't possible to try to understand whether this disagreement is in line with a disagreement in the large scale circulation changes or not. And for example, whether it might be interesting to define storylines of changes, of plausible future changes in compound flooding due to differences in the large scale circulation evolution. So I cannot really say. As you are saying, it might also be in principle due to, let's say, rare cyclones, which might lead to changes in opposite direction, but this should be investigated more, yeah.
All right, so Thomas Wall has a comment in the chat, partly answering the spatial footprint question. And then maybe Kalpana, do you want to ask your question, maybe explain a little bit what you mean by that?
Hello.
Hi, yeah.
Yeah, yes, I want to ask you about what type of preparedness is required in case of coastal flood? And is there any method to reduce the risk of coastal flood in coming future?
So sort of like how do we prepare for these types of coastal flood events?
Well, it's a question related, of course, to in general coastal flooding that is, I mean, not directly related to compound flooding. It's about, for example, preparing, improving dams, for example. I mean, in terms of compound flooding, it's sometimes even a bit more tricky, because you might, I don't know, build a dam which might protect you from the storm surge, but at the same time, this dam may not allow the water from the precipitation to drain into the sea. So in this case, and this is something that is developed already in part, I guess, in Netherlands, but at least might be thought better also for future conditions. In that case, you will need some pumps which are pushing the water from the inland side towards basically towards the sea. So when you think about compound flooding, sometimes the building up protection, it's even more complex. Yeah.
Thank you.
All right, are there any other questions for Emanuele?
Yeah, I have a question.
Yeah.
About the how do you deal with the modeling to deal with the pluvia and fluvia? Because when you got a levee along the river, and you may affect by the tidal or storm surge, but it affect the drainage in maybe inside the city or somewhere. Then how do you model it to show it? Because there's a compound flood.
So if I understood the question, you are asking how to take into account the interaction between the drivers, right? At a local scale.
Yeah.
Well, I mean, as you may well understood, in this case, we are really looking at a potential for flooding. So we are not really looking at interaction, at hydrological interaction between them. At a local scale, for example, I've worked on trying to assess the compound flooding at a local scale. So in that case, you may build something more accurate than what we are doing here. And we built through a statistical model. We modeled the water level in the joint area, which is a function of both storm surge and the river flow. River flow is influenced by precipitation, snow melt, temperature, and so on. And such a statistical model, which in that case was a simple regression model, allowed you to take into account the interaction between the two. There are, of course, more advanced models, which are basically hydrodynamical model, which can really take into account the non-linear interaction between the two in a more complex and advanced way. This kind of model are kind of developed currently because it's a kind of relatively new field of research, especially at a large scale. These models are like coming out basically the last like months. I hope this can help to answer to your question.
Okay, thank you.
Thanks. All right, cutting edge research. All right, so we'll wrap up the questions there, and of course, you know, since we're having the chat afterward, can talk in more detail with Emanuele at that time and casually. So now we will switch over to Danielle Touma for the second talk. Danielle is a postdoc at the University of California, Santa Barbara. Her research focuses on risks from extreme hydroclimatic events such as fires, mega droughts, and extreme precipitation, and especially multivariate and anthropogenic aspects of those events. And we're very glad to have her with us today to talk about the spatial imprint of greenhouse gases and aerosols on dry, warm, and windy fire weather conditions. So with that, Danielle, the floor is yours.
Awesome, thanks. I'll go ahead and share my screen. Okay. Looks good? Yep, okay.
Yes, looks good.
Okay, cool. Okay, so yeah, thanks for having me here. And thanks for Emanuele for your talk. It was really interesting. So today I'm going to be talking about my recent work looking at the anthropogenic impacts on extreme wildfire conditions. So as you just said, the dry, warm, windy conditions that cause fires. And this is work that I've been doing with Sam Stevenson at UCSB, as well as Flavio Lehner at University of Cornell and Sloan Coates at the University of Hawaii. So the reason we've been doing this work is because we've seen some unprecedented global wildfire events in recent years. Here are just a few examples of these events. The Amazon fires, which occurred last year, burned over 3,500 square miles of forest and released over 400 million tons of CO2. The Australia bushfires, which, believe it or not, only ended a few months ago, resulted in over 30 fatalities directly from the fires. But in addition to that, resulted in over 400 smoke-related fatalities. So kind of seeing these long-term effects of these types of really large fires. Currently, the Siberian peatlands are burning. Last time I checked, over 140,000 kilometers burnt. And they're also releasing lots and lots of CO2 because they store so much carbon. So this is a really significant impact on our climate and possibly causing a positive feedback loop. And lastly, currently we're experiencing some fires here in the Western US. And so far, over 30,000 square kilometers have burnt. This is the most area that has been burnt in the observed record, and we're not even done with the fire season yet. We've barely started. So, and this has already caused 35 deaths and a lot of poor air quality. So we might be seeing some of those smoke impacts over the next year or so. So these are just a handful of these events that have been happening in recent years. And if we zoom out to the past few decades, we see that this is also part of a increasing trend of burned area and frequency over the globe. This figure here shows just for the Western US, the burned area from the early 80s to just a couple of years ago. And you can see that in the early 80s, we would expect a given year to have around 5,000 square kilometers burned. But in more recent years, that number has tripled. As I said, we've already burned over 30,000 square kilometers this year. So you can imagine that if we continued this trend line, it would continue to increase. And the study by Bevacqua and Williams showed that the size of fire area on a given year is very closely related to how dry fuels are, as you can see in this very strong relationship. And you can see that more recent years, which are in red, have had drier fuels and larger fire areas compared to years previous to that that are shown in blue. So recent years have had drier fuels in addition to larger fires. That same study showed that these drier conditions or fire weather conditions were increased because of observed anthropogenic climate change. So everywhere where you see oranges and reds, which is all of the Western US, anthropogenic climate change caused fire weather to increase compared to a world without anthropogenic climate change. And in addition to that, a recent study by Michael Goss showed that there is also observed and projected co-occurrence of extreme fire weather conditions in multiple locations in California. So this study's focused specifically on Paradise and Malibu, where there were some large fires in recent years, and they showed, and the study showed that the co-occurrence of these two locations having increased fire weather conditions simultaneously is projected to increase in the future under anthropogenic climate change. However, we know that anthropogenic climate change is a combination of multiple forcings. Here is a figure showing the overall effect of different forcings over the last 2.5 centuries. So you can see that greenhouse gases has an overall warming effect, as we all know, while aerosols have an overall cooling effect, and land use change has had a slight cooling effect due to mostly albedo changes to the land surface. And we also know that these anthropogenic forcings, their effects change in both space and time. So you can see here the effect of aerosol forcing from 1930 to 1980 to the 2000. And you can see that both the magnitude and the spatial pattern of the cooling and warming effects of these aerosols change. So we wanted to ask, how do the different changing patterns of anthropogenic forcing affect extreme fire weather conditions? And so, so the main question we're asking here is, what is the impact of greenhouse gases, aerosols, biomass burning, and land use change on extreme fire weather conditions globally? So to do that, we use an awesome resource that is available from NCAR. It's this family of large ensemble experiments. And the ones that I use are the all-forcing experiment, which has more than 35 members, but I use the first 35 members. And it runs from 1920 to 2100 and includes all natural and anthropogenic forcings through time. In addition to that, there are simulations that isolate each forcing. So the all but aerosol forcing is a 20-member large ensemble experiment that includes all anthropogenic and natural forcings, except for aerosol forcings, which are fixed at 1920 levels. Similarly, there's a 20-member all but greenhouse gas ensemble, an all but biomass burning 15-member ensemble, and a 5-member ensemble for all but land use change. As you can see, the aerosol and greenhouse gas simulations have more members and run up to 2080. So I'll mostly be focusing on those anthropogenic activities and their effects on extreme fire weather. So to quantify extreme fire weather, I use the fire weather index. It's a widely used index that accounts for temperature, precipitation, relative humidity, and wind on daily to seasonal scales. And I use to quantify extreme fire weather, I use the 95th percentile as a threshold. So that's what I'll be talking about for the, that's what I'll be using for the rest of the talk here. So to quantify the impact of different anthropogenic forcing on the risk of extreme fire weather conditions, we calculate the risk ratio. And this is a ratio that divides the probability of extreme fire weather in the all forcing ensemble divided by the probability of extreme fire weather in the all but one forcing ensemble. So when the risk ratio is greater than 1, that means that forcing increases the risk of extreme fire weather. And when that risk ratio is less than 1, that means that that forcing decreases the risk. So here I'm showing the risk ratio for aerosol emissions for the period we're currently in, 2006 to 2029. You can see that currently aerosol emissions are reducing the risk over the Amazon regions, parts of Europe, parts of Africa, but they are increasing the risk over Southeast Asia and even Western North America and parts of Eastern North America too. So you can see there's a lot of spatial variability in the impacts of aerosol emissions on extreme fire weather. On the other hand, greenhouse gases has an overwhelmingly increasing impact on extreme fire weather in the current period over the globe. You can see that especially over the Amazon, and parts of Europe and Asia, there's a really strong, large increase, doubling in some cases, of extreme fire weather due to greenhouse gases compared to a world without anthropogenic greenhouse gas emissions. And so to kind of, so we see the spatial variability here, but to understand the temporal variability of these changes in risk, I'm going to focus on Western North America and the Amazon and dive into those a little bit. So here I'm showing a time series of the risk ratio for aerosol forcing for Western North America from 1920 to 2080. This is our whole experiment time series. And the solid line shows the median risk ratio of the ensemble, and the shaded region shows the ensemble spread of the risk ratio. So you can see that aerosols reduce fire risk in the 70s, but in the more current years and in the future, they're expected to slightly increased extreme fire weather risk. And we can talk about this more later, but this is because we expect for us to be reducing aerosol emissions in the future. So it's kind of counterintuitive, but that's what's happening. Oh yeah, so you guys know that if this line is above 1, it means that the risk is increasing. And if it's below 1, it means that the risk is decreasing. And now I'm overlaying the risk ratio time series for the other forcings. So greenhouse gases in red, biomass burning in purple, and land use land cover in green. And you can see that what stands out the most is this impact of greenhouse gases. And you can see that throughout the 20th and the 21st century, greenhouse gases increase extreme fire weather risk over Western North America. So we can compare this to the Amazon, which was the really dark saturated region, red region we saw on the map of greenhouse gases. And you can see that indeed this, the risk has already doubled and is expected to increase by around 7 times by the end of the 21st century under greenhouse gas emissions compared to a world without anthropogenic greenhouse gases. You do see for aerosols this kind of reducing impact. It's a lot smaller compared to that of greenhouse gases, but they do play a small role in reducing the risk of extreme fire weather. So we wanted to ask what is causing these large increases in the Amazon compared to these more subtle increases in Western North America. Not subtle, still a large increase, but smaller increases. So to dive into this a little bit, I'm going to show you how we isolated the effect of meteorological variables on extreme fire weather risk. So here I'm showing a map of extreme fire weather risk under greenhouse gas emissions for the later 21st century. So where you saw the Amazon extreme fire weather risk go up to around seven times compared to a world without greenhouse gases, and where you saw Western North America extreme fire weather risk increase by almost double. So to better understand these changes, we recalculated the extreme fire weather risk ratio by just accounting for changes in maximum temperature. So when we only account for changes in maximum temperature, we find that globally, extreme fire weather risk is increasing under greenhouse gases. And we do the same thing for the 3 other variables that we use for the fire weather index. And we find that for the Amazon, in addition to a maximum temperature increasing extreme fire weather risk, we find that decreases in relative humidity and increases in wind speed also cause increases in extreme fire weather risk. So over the Amazon, there's kind of this compounding impact of the different variables to increase extreme fire weather risk. If we look at the Western North America, we find that maximum temperature increases in maximum temperature does increase extreme fire weather risk over Western North America. However, increases in precipitation and relative humidity and slight decreases in wind speed kind of counteract that increase in extreme fire weather risk and cause the total change to be much smaller than that of the Amazon. So yeah, this is a small statement, which I already said, so I'll just keep going. So another thing we wanted to ask is how do these different anthropogenic activities impact extreme fire, the time of emergence of extreme fire weather, or how does it impact the time of new normal for extreme fire weather over the globe? Similar to a recent study, we found that in the all-forcing ensemble, around 74% of the burnable area over the globe permanently emerges above the historic natural variability by 2060. You can see that the time of emergence occurs much earlier for the Amazon region and parts of Europe, as well as Eastern North America. And so we wanted to ask, how do the different anthropogenic impacts activities impact this time of emergence? So we find that aerosols can delay this time of emergence over many parts of the globe, such as the Amazon, parts of Europe, and parts of Africa. So you can see that over the Amazon, this time of emergence is delayed by around 15 to 20 years. When we look at greenhouse gases, what we find is that when we don't include greenhouse gases, when we look at the experiment without greenhouse gas emissions, that permanent emergence does not occur. So everywhere where you see stippling here, that means that this time of emergence only occurs by including anthropogenic greenhouse gases. And so we thought this was a really interesting and kind of stark result. So while aerosols can delay the time of emergence, it's really greenhouse gases that are pushing the signal out of the variability. So I'll end here, and this is my concluding slide. Greenhouse gases increase the risk of extreme fire weather in the recent past and future periods, and they accelerate or even cause the emergence of extreme fire weather. And aerosols reduce extreme fire weather risk in many regions, but will have a smaller or opposite impact in the future. And yeah, so these findings we think can provide insight into mitigation and fire management policies as we go into the future. So I'll stop here and take questions. Thanks.
Thanks a lot, Danielle. So there are many questions already in the chat, and I'll just go from top to bottom. Michael Evans, who unfortunately left the chat already, but maybe others had a similar question to his, was wondering about the spatial patterns from the aerosols and the greenhouse gases, why they were different, and possibly his question refers to these opposite effects that aerosols can have depending on region.
Yes, where did I go? Oops. Okay. Yeah, I'll just go to that that first map that I showed. So we see that the extreme fire weather risk, the spatial patterns are different for aerosol emissions and greenhouse gases. This is for aerosol emissions. They can have a lot more local impacts. So it really depends kind of on the forcing scenario where aerosols are being emitted and where they're not. Greenhouse gases have a more kind of global impact. So they tend to change more of the large scale patterns of precipitation and temperature, relative humidity and wind. So they can have, they have just different kind of impacts based on the way they affect these different climate variables. Did that make sense? I know he's not there anymore, but
yeah, I guess so. I mean, there are many other questions, so maybe we can just go forward. So, Jakob, you had a question. You want to just say it out loud yourself?
I will try. I have a baby here, so but let's see. Yeah, so I was wondering whether you assessed how well the model represents the present day conditions, because presumably the model has a lot of biases and different variables, and this can strongly influence these risk ratios, right?
Yeah, I agree with you. I mean, there's a lot of literature about CESM already and how well it represents present day conditions. But for this study, we did look at what I'm showing here is comparing ERA interim fire weather index, the 95th percentile of the ERA interim fire weather index with the CESM all forcing fire weather index for 1980 to 2018. And on the right is I'm showing the differences between the two. And yeah, as you said, there are some discrepancies. One thing that we do, and you can see the one-to-one grid point by grid point comparison. Yeah, so we do see some biases in the model for sure when it comes to these this high threshold of the fire weather index. We do think that the spatial patterns are pretty well captured, but yes, the magnitude of the fire weather index can be much different from between the observations or reanalysis and the model. So definitely something to, definitely a caveat to mention.
Brian, you had a question on the scenario?
Yeah, so sorry I didn't mention that. This is under the RCP 8.5 scenario. So that's what all these experiments, these large ensemble CESM experiments are run with, are forced with. So it's the same, it's the same RCP 8.5 scenario for aerosols, land use change, and biomass burning as well.
Great, we have 2 more questions, and I guess then we should start to organize the breakout rooms. Merci. Do you want to unmute yourself?
Yeah. Hi. So I was asking if you assess the impact of the interaction between forcings, because when you assess a risk ratio, you're just adding a forcing, assuming that the other ones are present. So do you think that's impact?
Yeah, I'm not an atmospheric chemist, but I do believe that if there are some kind of, like if we kept like biomass burning, well, yeah, so we haven't assessed that, but I do believe that there would be, yeah, kind of these interactions between the different forcings, for example, aerosols and changes in, so the changes in temperatures with greenhouse gases might impact aerosols, for example. But yeah, we always assume that all other forcings are present when we do the all but one, when we compare them. Is that your question? Sorry.
Yeah, that is my question.
Yeah. So I definitely think that we would have a different kind of outcome if we did like all but 2 or all but 3, or, you know, but I think, yeah, in the study we were isolating just one at a time.
Okay, thank you.
Okay,
yeah,
thanks. So I see the last question was rather a comment, and
yeah.
that's why I would yeah, start off with the organization of the breakouts